Today, we are going to study the symmetries of phase space for an arbitrary finite number of dimensions. Let's get started. The one thing that we have been doing so far has been explicitly using momentum and position coordinates when describing phase space. And this has the added benefit of being more intuitive to interpret physically, but it obstructs our ability to fully understand the full symmetries of the Poisson bracket and of phase space. So to that end, right now, we are going to take a more symmetric approach. Fair warning, the complexity of the arguments in these next couple of sections grows a little bit, so let's keep our wits about us. Let xi, the variable xi, the Greek letter xi, represent a vector on phase space, and let's use the direct sum construction of position and momentum seriously so that the vector xi can be basically thought of as the position coordinates stacked above the momentum coordinates. By the way, these beautiful eggplants come from my friend Joey's garden. Thanks, Joey. In addition to the coordinates taking that kind of structure, we can also think about derivatives. Specifically, we can think about the gradient in phase space as being stacked. And just like in ordinary three-dimensional space, we can consider the gradient of a scalar function to be a vector. More precisely, these are vector fields because they have continuous variables that vary with the function all over phase space. But whatever, same architectural thing. In fact, as much as possible, you're going to want to pull in all of your intuition from ordinary three-dimensional vector calculus, vector analysis, vector algebra, whatever, the whole thing. It'll all serve you pretty well. We've been working a lot with functions on phase space for a while now, so gradients of them are hopefully nothing new. In particular, we've been studying the spatial gradients of, for example, the scalar potential. But now we're asking you to consider gradients in the full phase space sense. Perhaps the most important function to consider the gradient of is the energy function. We are kind of familiar with derivatives of the energy function already, so let's go ahead and look at explicitly, in terms of P's and Q's, what the gradient of the energy function actually looks like. Just looking at it as a vector, we already see that it looks kind of like the Hamilton equations, but things are just a little upside down. So to remedy that, let's define a matrix. Let's define this matrix J, which is kind of like block antisymmetric. To get a sense for how J works, or to get a sense for the properties of J, let's sandwich it between two copies of xi, the coordinate vector on phase space, right? So xi transpose J xi and see what we get. Of course, xi is antisymmetric, which means that this whole thing is going to be zero, but it's important to look at how it gets to zero. So in terms of the block Q's and P's, we get Q's times P's minus P's times Q's, which, yes, is zero, but if you've studied quantum mechanics, hopefully it is zero in a way that is very interesting to you. In any case, we can take that matrix J. Oh, too dark. In any case, we can take that matrix J and multiply it by our gradient of the energy function, and lo and behold, wouldn't you know, it gives us something back that looks a lot like the Hamilton equations stacked on top of each other. And so, armed with that, we have a more compact or more symmetric way to write the Hamilton equations down. Now this is great, but previously we've seen the Poisson bracket used as a proxy for the time derivative. And so you might ask, okay, how can we take the time derivative of any function a? What would that look like? And of course, to do that, we have to uncover where the Poisson bracket is in all of this stuff. But once again, J comes to the rescue. Consider for a moment the gradient of two separate functions a and b. So now we have two vectors. Well, let's play a similar game. Let's now surround the J matrix with these two vectors. That is to say, we'll take grad A transpose dot J dot grad B and see what we get. Well, the obvious first thing is that we're going to get anti-symmetrized derivatives. And if we expand this in terms of the P's and Q blocks, yep, you got it. The Poisson bracket is back. We have traded the Poisson bracket for a sort of matrix multiplication, kind of inner product sort of operation on the gradients of the various functions. And for those of you following that whole differential geometer story about the two form, the symplectic two form or whatnot, hopefully this gives you now a clear and concrete presentation of how that two form is constructed. J, in other words, encodes the details of the Poisson bracket, and more broadly, it encodes the details of the dynamics, the physics on phase space. J, in some sense, is our fundamental object of study. For these reasons, we call J a symplectic matrix, which is going to get confusing in terms of terminology because there is a group of symplectic matrices, none of which are in fact J. But now that we have our technology, our symmetric representation of phase space, let's proceed to analyze its symmetry. We are now in a position to understand the symmetries, the linear symplectomorphisms of phase space for arbitrary finite dimension. Let M be any invertible matrix, that is to say, any matrix in the general linear group of matrices that act on phase space. In general, M can act on any vector in phase space, and in particular, it can act on a gradient. So let's do that. So let's assume that M is fixed, it's constant, and let it act on a gradient of a function A. Actually, to be more precise, let it act on a function A and a function B, and let's throw those two functions into our new representation of the Poisson bracket. So we take M grad A transpose multiplied by J multiplied by M grad B, and following the rules of transpose, right, we flip things backwards in a transposed way, we get grad A transpose, M transpose, J, M, grad B. And if this linear transformation M is really going to respect the Poisson bracket, then it is necessary and sufficient to show that M transpose J M must be equal to J. That is to say, this whole left-hand side must be equal to what it used to be, grad A transpose times J times grad B. Which is awesome because now we have something to aim for. Specifically, we can look for the matrices that are invertible that satisfy this particular matrix condition. In other words, our matrix J gives us a condition to find which other matrices serve as symmetries of phase space. In fact, this is going to be our defining relationship that determines the so-called symplectic group, the real symplectic group of matrices, SP2NR. Those are the invertible matrices that satisfy that condition. First, let's go ahead and prove that this is in fact a subgroup of GLP. Proof. For any M and N in SP2NR, we can of course compose these two matrices by multiplying them together using the standard matrix product that descends from GL to NR. So let's go ahead and do that and act on the gradient of A. And similarly, we can act on the gradient of B. And we'll put these two things into our new version of our Poisson bracket, and we find the condition on this product matrix, Mn, is given by Mn transpose times J times Mn must be equal to J. But by the rules of transpose, of course, Mn transpose is N transpose times M transpose. And so we see, because M and N are both members of SP2NR, they satisfy that particular condition. So the middle contracts to just J from M being a symplectic matrix, or some member of the symplectic group, subsequently n does as well, and so therefore their product does. And so the product of any two matrices that belong to sp2nr are in fact in sp2mr. Hopefully it's clear that the identity matrix is such a member, and I'll let you figure the inverse part out on your own as an exercise if you like. To show that this subgroup is a proper subgroup, we need only take the determinant of both sides of the defining equation. We immediately have the fact that the determinant of m squared is equal to 1, which means that the determinant of m, at least at this point, is plus or minus 1, which is sufficient to show that, yeah, indeed, it is a proper subgroup, as matrices in GL2nr can have pretty much whatever determinant they like, as long as it's non-zero. But in fact, we can say more. Indeed, we can take the Pfaffian of both sides, because J is an even dimension, like a 2n by 2n antisymmetric matrix. And so the Pfaffian of the right-hand side is 1, the Pfaffian of the left-hand side is a little involved. I'm not going to go through the proof of this following claim here, but suffice it to say, when you conjugate a matrix of the form J by an invertible matrix of the form M, you get the determinant of M times the Pfaffian back. So in other words, the determinant of M times the Pfaffian of J is equal to the Pfaffian of J, which means that the determinant of N is necessarily 1. And so we have shown that the group of symplectic matrices sp2nr is a subgroup of SL2nr, the special linear group, the group of matrices that have a unit determinant. So now, another proposition. We're going to claim that the matrix group sp2nr is a proper subgroup of SL2nr for the case where n is greater than 1. You remember last time how we showed that having determinant 1 is a necessary condition for being a linear symplectomorphism, but not a sufficient condition, and it is only sufficient for the case of SL2R? Well, here we go. Well, we know that sp2nr is a subgroup of SL and 2nr from our previous discussion. Great. So to show that it's a proper subgroup, all we need to do is find an example that exists in SL2nr and does not exist in sp2nr. And a great example of that would be let x and y be two coordinates in physical space. So they have associated momenta px and py. Let's consider the matrix that rotates x into y, but leaves the momentum alone, right? So I can just write that matrix here. That matrix has determinant 1, but that matrix does not satisfy the condition for being a linear symplectomorphism. Ergo, there exists at least one element of SL2nr that is not in sp2nr, and so it's a proper subset, and therefore it's a proper subgroup. Today we spoke a lot about the symplectic, the group of linear symplectomorphisms, matrices in the symplectic group. We talked a lot about it at kind of the bird's eye view scale. We haven't really discussed much about details by way of example or anything like that. We will fix that soon enough. But I think I've spoken enough for one day, so let's punt that for next time.